All right, hopefully pretty quick and painless on this. We're going to find the area for parallelograms and also the area for triangles in this first lesson of our new Unit 7. The learner will hopefully be able to find those areas by applying the formulas that we are going to show here momentarily. These formulas will look familiar, although when we've found the areas for parallelograms, we've been pretty limited in our work to just dealing with rectangles and squares. And now our formula is going to be the same for all parallelograms. When dealing with a triangle, this formula will look a little different than the 5th grade version where you have base times height divided by 2. Instead, we're going to write it as 1/2 times base times height, just to reinforce that usefulness of multiplying by a fraction and just kind of writing that formula a little bit differently than how we did in our elementary days. So the area of a rectangle is simply found by taking the length of one of the bases by the height. And so this formula, we're pretty familiar with that from the standpoint of working with a rectangle, that the area of a rectangle is base times height. But this is true for all parallelograms, all right? When we are talking about rectangles, it's pretty easy to identify one of the sides as base and then one of the other sides is the height because the sides are perpendicular to each other. With a parallelogram, the sides are not perpendicular, so we do not just multiply the lengths of the sides together. Rather, the area of the parallelogram is the product of a base and then the corresponding height. So it's the same formula, but the b and the h, they still mean the same thing. It's just that they are applied differently. So let's have a little bit of the anatomy for a parallelogram. The first thing is to recognize that any one of the sides can be a base in a parallelogram. It does not have to be the quote-unquote bottom of the parallelogram, depending on how your paper is oriented, all right? If you turn your paper 90 degrees, any one of the sides could be the base, all right? And so that's kind of the point there in dealing with the bases of a parallelogram. In addition, there is a segment that is drawn perpendicular to the base, all right, or perpendicular to the line containing the base. And it connects to a line containing the opposite base. That perpendicular distance is referred to as the height, all right? So the segment that you would draw between those parallel sides is called the altitude. But the distance, the length of that altitude, the distance between those parallel sides in the parallelogram is called the height of the parallelogram. All right, so in these pictures, as you are looking, you can notice that maybe the bottom of each of these parallelograms can be the base. So this is 5 inches, this is 2 inches, but then that perpendicular distance between these parallel bases is the height. All right, so this 4.5 inches is not the height, 4 inches is the height. Over here, this segment is 2 inches. We don't know anything about this. But this distance is 3.5 inches, all right? We're not going to take 2 times 4.6, we're going to take 2 times 3.5. We're going to take 5 times 4, not 5 times 4.5, all right? So this is the perpendicular distance between these parallel bases. If this were my base, I'd have a different distance, and we'll talk about that here in just a moment. But here's how we're going to find the area for these parallelograms. Essentially, we're going to write the formula, we're going to substitute the values, and then we're going to compute the area there. So the area here is the base in inches times the height in inches, which means that we get a total of 20 inches times inches. Whenever we multiply something by itself, we call that squaring. So we end up with inches squared, or square inches, for the area. Your work should look just like this. You write down the formula so that you learn the formula. You plug in the numbers so you know what you're supposed to do using the substitution property of equality. And then you do your calculation or computation afterwards. Again, the area here is the base times the height. So in this case, it's 2 times 3.5. And that gives us a total of 7. And again, it's inches times inches, so that makes inches squared, or squared inches. Keep in mind how we write this. We're squaring the units. We're not squaring this number. It's the inches times the inches. When we speak it in English, we say 7 square inches, but it's not 7 squared inches. It's 7 square inches. So you want to be mindful of the language and how that influences the way that you write. Please do not write that as 7 squared and then the word inches, because then you're going to call that 49 inches. And that is not the case here. So be aware of that. Be careful of that. Make sure you're doing a decent job with that. We're going to skip this example. We did not work in the coordinate plane in Unit 6. We will not do that in the coordinate plane here in Unit 7. And so here is a different example. This is example 3. We skipped example 2. Here's a situation where we know a base and a corresponding height. We know a base, but we don't know the length of the other altitude, all right? And so our job is to find the length of segment CF. This is, again, the altitude. Segment CF is the altitude between these parallel sides. And we can call any one of the sides the base. In this situation, how we're going to approach that is recognize that I have a base height combo right here. I have a base. I have an altitude's length given. We call that the height. And so I can compute the area of this polygon, of this parallelogram, using our base times height formula. And again, I'm working with inches. Sorry that these are all the same units. We can verify or vary that as much as we need to or want to. But this tells me the area of this parallelogram. Taking this base times this height gives us this area. Now, what I want you to think about is if I had to take this base times that height, shouldn't I get the same area? If it's the same picture, then it doesn't matter how it's oriented or how it's rotated, it still has the same area. The question is, what happens when I take the other base of 13 inches times the unknown length of segment CF? All right? Well, we get the same area of 120 square inches. All right? The question, though, is what actually is the length of segment CF? And so we have to actually do division. Now, 120, it doesn't divide by 13 very nicely. All right? I get this crazy decimal answer, 9.23, blah, 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 blah. It says to the nearest tenth. So I'm going to say, when I divide both sides, I'm going to say 9.2 is approximately equal to the length of segment CF. So we're using that same notation for the length of a segment that we used in Unit 1. The approximately symbol that we used here and there between Units 1 and 4. And then, of course, there is the decimal answer to the nearest 1/10. It was 9.23. The 3 tells us to round that down to 9.2. We were able to compute the area easily of this figure to say that it's 120 square inches, but then we use that area to find the length of the other altitude using the other base. The next part of our lesson deals with the area of a triangle. Now, like I said, this looks a little bit different than the 5th grade version of your formula. It's the same thing. I want to encourage you to have a high school understanding of the area of a triangle. The area of a triangle is half the product of the base and the height. Basically, every triangle is half of a parallelogram. All right? Every triangle is half of a parallelogram. You can take any triangle, and you're trying to find the area of it, and you can recognize that it is half of a pair of congruent triangles, all right? And those congruent triangles together make a parallelogram. And we know the area of this parallelogram is going to be the length of one of the bases times the length of one of the heights. And so we can simply understand that when I find the area of this parallelogram, if I cut that parallelogram in half, it's going to give me half of that parallelogram. Is going to give me the area of the triangle that is remaining. So the area of a triangle is 1/2 times the base times the height. And so in these cases, when we're dealing with right triangles, a base and a height could be either of these sides. The 13 here, if I want to do a squared plus b squared, it gives me c squared. That's fantastic. But I'm not going to use this in computing my area when I have 5 times 12 and times 1/2 as our possibility. Just like with the original example, we're going to write down our formula. Part of the reason I ask you to do that is so that you can learn those formulas. Obviously, when they're easy formulas that you know already, it seems like extra work, but I want it to be a habit that you establish for when the formulas get a little more difficult. So the expectation on all of our classwork and all of the homework is that we are going to be able to take, in this case, half of 60 to get 30. And again, we're in centimeters. The expectation I'm going to have for you in your classwork is that you write your formula, you substitute your values, you compute using your calculator or your brain. Over here in letter B, same deal. Go ahead and try that without me. Pause the video. Should have been able to find that we take the base. This is the actual base. This is not part of the base of this triangle. These are extending out the side so that we can find out what the height is with reference to that base. So 10 times 6.4, these are both measured in feet. So I get that the area is half of 64, which is 32. And this is square feet, like I said. All right? Computing the area of a triangle is, again, I know it's something that you've done before, but I want you to use this high school version of that formula. It sounds trite, it sounds silly, but it's going to help you connect the ideas for why and how we derive the formulas for our other figures that we're going to be dealing with in this unit, be they regular polygons or kites or trapezoids. And so we're going to use that information, that formula, to help us derive those others. That is the end of this 7-1 lesson.